And we're back. I left on a kind of cliffhanger, whatever. Mr. and Mrs. Hanger Ending and their son Cliff Hanger Ending. Old jokes. Well, yeah, very old jokes. Welcome back. Thank you for coming back. If you haven't come back, you can't hear this, so you're missing out on a lot, and that's your loss, and I don't care. It's still Rob Miles. It's still writing games with C# and XNA, and it's still exciting and dangerous. We're going to actually mend something this week. Last time, we actually broke something, so mending seems reasonable. We had a broken Moodlight. If you remember the story so far, ... dun dun dun. I think I'm in a good mood tonight, not quite sure why. I think it was I had lasagna for tea. Very nice it was too. Lovely. We try to make a mood light that fades up from dark to light. And we've got one that flashes. It doesn't actually really flash particularly well, but more of that in a moment. But the way we made it work was we increased the... that was a chair. Sorry about this creaky chair. We increased the brightness of the red, green and blue bits, and we just kept on making them brighter and brighter and brighter. And that bit worked fine, but then suddenly, for no reason at all we can see, it goes black again, and this we really need to fix. So the idea was that we've got this theory, this mechanism we're using to manage the colors on our screen, and we know the bigger the number, the brighter the color. And so what happens is that we have a program that does this, and I will now, without the aid of acupuncture, I'll just slide across to my program that shows this. We've got our program called Moodlight. Quick recap here. Here's the program code, which I'm going to go gently through. 3 values, one called red intensity, one called green intensity, one called blue intensity. And these start off at 0, which means black. Okay. Each time the game goes tick, each time update runs, if I drill my way down into here, I make the red intensity 1 bigger because that's what ++ does, and I do the same with the green and the blue. Okay, sorry, that's not the right bit, that's a bit there. So every time we get updated, we get brighter, and then down in the draw part of the country, having made a color from the red, the green and the blue that we're updating each time, we drew the screen that color. So if I now run this, you'll see that we get a screen that's black, gets brighter and brighter and brighter and brighter and brighter, and then goes black again. And it goes through this, and what I really want is a mood light that behaves a little bit less sort of suddenly, a little bit less sort of abruptly at the end of its brightenings. So I'll stop that. Okay, and I'll hit the magic keys that take me back to the presentation. There we are. Okay, so we've seen it. The brightness values increase 60 times a second. That number is actually quite significant, as we'll see in a moment. And it uses this version of update that actually changes the brightness each time we get a tick. And as the unsmiling little face there says, the screen gets brighter and brighter, and then it goes black. And it happens around 4 seconds or so. Everything else seems to work, and the program, and this is interesting, remember this one folks, the program doesn't complain. The computer keeps going. It doesn't say, something bad has happened here, Captain. On Star Trek it usually involves the self-destruct system, but on this one it doesn't do that. It just keeps going, and the screen suddenly goes black. So what's happening? Well, what we're doing now is we're debugging, and when we start to debug programs, our detective person appears with a magnifying glass and a trench coat. We're trying to work out what would happen to cause the screen to go black. Now debugging is a bit like detective work, because you arrive at the scene of a crime, a broken program, and you have a bunch of evidence, people looking guilty and staring at their shoes and stuff, and you want to figure out from the evidence and the people and everything else what it is that's gone on, and who the murderer is, and why the murderer was. Happens in CSI every week, as far as I've discovered. So we want to do that with our program, okay? So a bit of detective work to find out why our program is behaving the way it is. We know that in terms of evidence, smoking guns and all that, the screen is black when the color intensity values are 0. So something must be making our color go back to black again, and that's the thing we need to investigate. Something's causing the intensity to suddenly go from really bright to really dark, from a bright value to 0, because 0 is what causes the black to come out. Okay, so update is called 60 times a second, we know that. Each time it's called, the color gets one bigger. Every 4 seconds or so, the intensity values go back to 0, and that's as if they're full. They can't take any more. They're actually, there's no room in the variable to actually hold the value we're trying to put in there. And if we go way back into the past, slide 7 of one of the presentations, so it says here, when we looked at bytes, we said, yep, they use 8 bits to hold a number. Now, if you know much about binary arithmetic, and there's no particular reason why you should, I do, because I've been doing this for 30 years, and so I really should. A byte uses 8 bits to hold a number. Now the way that these things work, each time you add a bit, you double the number of possible values, okay? So if we think in terms of 1 bit, that gives us 2. If we have, that's either on or off. If we have 2 bits, that means we've now got an on and an off and another on and another off, which means effectively we double the number to get 4. The 3rd bit takes us to 8. 4th bit to 16, and so on. Get to 8 and you have 256 possible states in a byte, of which 255 can be used for numbers because the one at the bottom is 0. If the program tries to increase a byte value containing 255, it will overflow and wrap around to 0. In other words, there's no more bits to hold the information, so effectively everything goes around. And just to show that overflow really is happening, I've put a picture of a full bath. So that's guaranteed. I mean, it all makes perfect sense, and the bath is full. So you're really getting a proper in-depth explanation here. But the bottom line is that any given value in the computer's memory has a finite capacity, just like your bath, just like any container object. And if you try and put stuff in, it isn't like a bath. The bath doesn't suddenly empty when you put that last little drop in. But in the case of computer bytes and data values, it's like the straw that breaks the camel's back. You put that one little extra bit in, and it doesn't sort of stop taking any more. It flips right round back to 0 again and wraps around. This is called wrapping round. It's what your car would do in the old days. If you drove your car hundreds of thousands of miles, eventually the mile counter in the speedo, the thing that tells you how far you've gone, will go back round to 0 again. And that's what's happening here. So we add 1. And rather than getting 256, which is what we should get because the sum is an addition, we get 0. And that's just a side effect of the way that computers hold data. But the thing that's kind of scary, and I want you to remember, is that we didn't get an error. The program did keep going. It didn't do what we wanted, but it did keep going. This introduces a rather sort of scary type of error into a situation called a runtime error. In this particular case, it's the worst kind of runtime error, and it's one that hasn't been spotted. It's one that we didn't notice. It's one the system didn't pick up, and that makes it a little bit dangerous. And we'll talk about how you can fix this and what other things happen a bit later. So don't worry too much, but do bear in mind that not everything that goes wrong in your computer will be noticed by the computer, because that's what's happening at the moment. Okay, so there you go. This is like a little diagram that sets it all out. If I have a single bit, I can hold 2 values. If I have 2 bits, I can hold 4 values, then my 8, then my 16, go all the way to 1, 2, 3, 4, 5, 6, 7, 8 bits, and I get to 256. Okay, take away the value we need to use for 0, and you have 255 possible different values. And so what happens is I've got 255, which is all my red bits here turned to red. 254 was everything but the last bit. 255, all the bits light up. If I add another bit, it would like to sort of set that bit there, but there isn't one. So all these ones go back to 0, and suddenly my screen goes black. It's called overflow. As far as computers are concerned, we've seen that, we've seen the bath, we know all this. It's overflow that's happening. It's overflow that's causing the problem. So we're going to have to make our program work and not do this. And as the slide says here, this is the kind of scary thing, because sometimes a bug in your program causes it to fall over. Sometimes it doesn't. It just does the wrong thing. You can't rely on the computer to notice when things are wrong. Okay, computers don't care. You have to program them to care. Okay, the stuff just happens, and the program will actually keep on going in some situations. So just because it's wrong doesn't mean to say the computer will notice that. Computers don't really have that. It's the program that you put in that makes them care about what's going to happen. Okay, So actually, if you think about it, we can't just keep on making the light brighter. This won't work in real life. If you turn the brightness knob on your TV up as bright as you can, that's as bright as it goes. We can't, otherwise the thing will just get so bright it would get brighter than the sun, and it's quite a good science fiction short story in there, I suppose, but it wouldn't happen in real life because your TV and everything, they'll have limits to how bright they can go. So what we're going to do for now, just to fix the problem in the first place, is make the light fade up slowly, and when it reaches full brightness, stay there. Okay, so what we have to do is stop the light from actually doing this nasty flash. Just make it fade up to a nice steady light. Okay, a kind of soft start, if you like, a nice sort of gradual fade up. And to do that, we have to make a decision in the program. The program has to go, oh, I can't add 1 to the value anymore because it's as big as it could possibly get. So the program has to actually make a decision when it runs. This is what computers really exist to do. And the thing that makes a computer really powerful is the fact that it can look at something and make a decision based on those values and then do something different depending on the situation. Because once we've got decision making built in, we can make programs that are really, really useful. And these things in programming terms in C# are called conditional execution statements or conditions. And the idea is that you do something if the test is true, or you don't if the test is false. Okay, so let's look at a bit of conditional here. Bit of stuff. If is a piece of C# that says to the compiler, hey, a test is coming down the tracks. Okay, the test is actually given in the 2 brackets here. Red intensity is the number that holds the brightness of our red value, and we're comparing it with the value 255, which is the biggest possible white bright number we can have. And what this little testing thing does here is it says if the intensity is less than, that's what this little arrow thing means. If you've done maths, you'll know about that. I know it's less than because it looks a bit like an L. It stands for less than, you see. So if red intensity is less than 255, I'm allowed to add 1 to it. So if this condition is true, this statement is performed. But when red intensity reaches 255, in other words, when it's equal to it, it's no longer less than, the condition becomes false, and the sum stops happening. Okay, so as soon as red intensity reaches 255, we've kind of capped it. We've put a limit on how bright it's allowed to get, and so this little condition will mean that our lights will get brighter and brighter and brighter, and then stop. Okay, if you look at the thing and break it down, then what we've got is a value, which is the variable we're looking at, a logical operator which performs the actual comparison, which in this case is my less than, another value which is being compared with, and then a statement that we get obeyed if the condition is true. So this here will only actually allow me to make my intensity bigger up to a limit of 255. It's a bit like if you had an employee and you say, I'll pay you a bonus up to £200 but no more. And when the bonus hits £200 or whatever, no matter how much extra he doesn't get more than the biggest bonus. Same kind of thing here. We're capping the value of red intensity. That's how it works. And so what I can do now, if I go into my compiler again, just drop back to here, I'm going to go and fetch my fixed version of the Moodlight, which is here. Okay, and this one, if I take a look at the code, have a look in game. Okay, we wheedle my way down here. Right, I've got 3 versions of the test. If the red is less than 255, make red bigger. If green is less than 255, make green bigger. If blue is less than 255, make blue bigger. Otherwise, when they reach that value, they won't get changed. So if I run the program now, it fades up to white, and then it stops. So now we've actually got the values as bright as they can be. The system is actually sort of stopped at that value, and we don't get the flash because every time we go around this program statement now, this one's 255, so that doesn't happen. This one's 255, that condition fails as well, and this one's 255, and that condition fails too. So we've mended it, is the simplest way of putting that. So the idea is that I can now make a decision based on the contents of a variable, and I can start to do kind of interesting things based on that. So if we drop back here, I've fixed my fading up thing, I'm a happy bunny, all is well, and we have a nice fade up, at which point the light stays as bright as it can. So what have we learned? Well, we've learned that data in computers is stored in bits that can hold two values, but we actually store larger than the value 0 or 1 by stringing these bits together. And people talk about their machines having so many megabytes. A byte is actually a lump of data 4 bits in size. So that means we can hold numbers in a single byte that go from 0 to 255. If you try and put a value in that's more than that, it ain't going to fit. You're going to have this overflow thing, and it all wraps round and goes back to 0, at which point your program will not work. It'll do bad things. But as we have seen, the computer will not always pick this up. As far as the program is concerned, it's tried to do its best. The number's fallen off the end, and I'm afraid, bad news just in, that's your fault, because you're the programmer that's supposed to get these things correct. However, the good news is you have a tool that lets you make things correct by putting in conditions that can look at the values in variables and make decisions based on those values to keep things running nicely along. Okay, so the whole business of computer programming is making the decisions based on the values coming in, so your program actually runs along nicely and does what it's supposed to do. Okay, so true or false? Here we go. A byte can only contain 8 values. I don't like that. It's got 8 bits in it, but as we've seen, it can go a lot bigger than 8. It can go all the way up to 255, so that, I reckon, will go red. Aha! A bit can only hold 2 values. Well, I reckon that's true. Sometimes they call these things true or false, or 1 or 0. In terms of the actual circuitry, it usually means the thing has a voltage on it or not a voltage, plus 3 volts or no volts at all. We don't have to care about that. That's hidden from us by the hardware and everything on top of it. But the bottom line is that a bit can hold 2 values and no more. When a value overflows, the computer stops running. Well, we've done that, and the computer kept going. So I think that's false, and by gum, I'm right. It's almost as if I'd written these questions and decided the answers before I did this. Who would have thought today? Next one. A conditional statement executes a statement if a condition is true. I like that. I reckon that's true. So we get green. And the bottom one, this is a bit scary. Ooh, a conditional operator is used to add 1 to a value. Well, when I hear the word condition, my brain sort of goes, ooh, test. So conditions to me mean I'm performing a test to decide whether something is true or not. I'm not doing any kind of sums. So I reckon that conditional operators don't add anything to anything. They're just there to allow me to make comparisons between stuff, which I can then use to drive my decisions. So as far as I'm concerned, that statement should be false, and is. Okay, so we've mended our Moodlight in that we now have a smoothly fading one that goes all the way from dark to bright and stays there. If you've ever wondered how things are made to fade in computer programs, you now know, because they use just the same trick, get it brighter and brighter and brighter and brighter and brighter. There's the brightness they want, at which point they actually stop, and at that point they've got the light that they need. Okay, so it all hangs together quite nicely. Thank you very much for paying attention and sticking with the suspense for all this time. Next time we're going to move on and do even more things with our Moodlight, and I'll see you then. Actually, no, I won't see you then, and you won't see me. Kind of a stupid thing to say, but we'll meet up somehow, I'm sure. Thank you.